Hey everyone, this is question 17 and it asks, a particle of mass m is shot with an initial velocity v initial making an angle theta with a horizontal as shown. The particle moves in a gravitational field of Earth. Find the angular momentum in a particle about the origin when the particle is A at the origin, B at the highest point in its trajectory, C just before it hits the ground, and D what's the torque that causes its angular momentum to change. Okay. So, question 17. Question A, it asks for the angular momentum, which can be represented as R cross momentum, or moment of inertia times angular velocity. Now, angular velocity and moment of inertia both have a separate formula, and actually makes the problem really, really confusing. So I chose to just use this one and not that one for this problem. First, the vector r, when it's at the origin, would be 0, 0, since nothing has moved. And whatever the angular, the momentum might be. If you multiply a 0 vector times anything, you're gonna be stuck with 0 as your answer. So the angular momentum when the object is at the origin is going to be 0. Now for the remainder of these questions, you're actually going to need to know the distance between here to here, and from here to here. Now obviously from here to here is going to be, the distance is going to be double from that from here to here. So I'm just going to set up a kinematics chart for this section right there, when the object would be at its highest trajectory. So x, y, acceleration, delta t, delta x. Okay, you know that this is going to be vi cosine theta, and this one's going to be vi sine theta. This one's going to stay vi cosine theta at the highest point. The y is going to become 0. Acceleration is going to be negative g, or negative 9.8 if you prefer. And acceleration in the x direction is always 0. Delta t you don't know, and delta x is what you're trying to find. So we will start with v final is equal to vi plus acceleration times time. And this is for the y. So z is equal to vi sine theta plus acceleration, which is negative g, times time. So time, that must equal to vi sine. It's going to equal vi sine over g, and that is time. So then for x, delta x is going to be equal to v naught t times 1/2 acceleration times time squared, which is then equal to vi cosine theta plus times time, which is going to be vi sine theta, g, plus 1/2 acceleration is 0, so t squared, whatever, because that is going to become 0. So then, you know your displacement in the x direction is going to be vi squared sine theta cosine theta over g. Now for displacement of y, I'm actually going to use this formula. It's going to be velocity final squared equals vi squared plus 2a delta y. You know velocity final is 0, vi squared sine squared theta for initial squared, plus 2 times negative gravity times change in y. So then change in y becomes vi squared sine squared theta over 2g. So now back to the original question, which said L, find the angular momentum, which is r cross p. Now we know that p is also mass times velocity, where mass is a scalar, v is the vector. r we know is to be x here and y there. So vi squared sine theta cosine theta over g, vi squared sine squared theta 2g cross, oh, and that's how I write my vectors. You can write this as I and that as j. Cross mass, which we do not know, and velocity. Velocity there we know to be at the final point. Here, it's the I, the j. So vi cosine theta, comma 0. If you expand it a bit, it becomes like so. Now, if you find the cross product, which would mean this times this minus this times this, you end up with...
Sorry, I didn't understand the question I heard.
You end up with mvi cosine theta times vi squared sine squared theta 2g, and this would all be negative because it's this minus this, that. And that is your answer to B. If you simplify it further, this is what you get. Okay, now we're going to do question C. Question C is something very similar. Question C. L is R cross. Momentum is... Now, at this little end of the fall, the distance in the x direction will be double here. So your R would be equal to 2 times vi squared sine theta cosine theta. But your y from here to there is a 0. The change is 0. So this becomes your r vector. Now your velocity is going to be slightly different. Velocity final is equal to v, and this is the y only, squared plus 2ax vy squared sine squared theta minus 2g times 0, because the change in the y direction is 0, gives you that vy is equal to negative v final, like so. And you know that the vx does not change throughout, so that component will stay the same. So your velocity then becomes vi cosine theta, comma, negative vf, or vi actually, sorry, sine theta. Oh, it's because I got myself confused. Okay. When this is done, you get, when you multiply these two with m, of course, you get vi squared sine theta cosine theta g comma 0 comma vi cosine theta negative m vi sine theta. If you find the cross product, this minus this, you will be stuck with negative 2m vi cubed cosine theta sine squared theta over g. Oh, and the direction is k for both B and C. Okay, and that's your answer. So now the final part of the question asks, in part D, what torque causes the angular momentum to change? Well, in this little course that it takes, there's only one force besides the initial external force, and that's gravity. So gravity pulls the object downward, and therefore causes a torque in the negative z direction. Okay, and that's question 17. Thank you.